Hello everyone. So today we're going to go over section 11.2, Analyzing Rational Functions, part 2. So in the first example here, we have a rational function with given asymptotes and a point of discontinuity. There's a vertical asymptote at x equals 2, and a horizontal asymptote at y equals to -3. The coordinates of the point of discontinuity are 6 and -5. We can see from the graph that the form of the function is going to be y is equal to a over x minus h plus k. And in this case, h is going to be equal to 2, and k is going to be equal to -3. And that's because of what we know about the asymptotes. So to find a, we're going to use the point of discontinuity and substitute it directly into the function as it is right now. And then we can solve for a. And so a is going to be equal to -8. So if we put everything together, we get y is equal to -8 over, oops, sorry about that, x minus 2, and then -3. However, we still have the point of discontinuity at 6, -5. So in order to account for that, we need a common factor in our rational function. And a common factor will be x minus 6. So now we have the equation for the rational function that's graphed right here. And that's it. So in the next example, we are looking at matching graphs and equations for rational functions. So to do that, what we can look at is to factor each function. So for a of x, we can factor out x in the numerator and factor the difference of squares in the denominator. So because of the common factor, we know that this function will have a point of discontinuity at x equals 2. Sorry, x equals -2. And an asymptote at x equals 2. Which means a of x must be graph 2. Secondly, we have b of x, So notice that we can still factor. We can factor out 2 from the numerator. However, the denominator cannot be factored. Also, if we consider the denominator, we'll find that it's never equal to 0. As such, b of x has no vertical asymptotes. Which means b of x must be graph 3. Finally, we have c of x. So here we have 2x over the difference of squares of x plus 2, x minus 2. So since there are no common factors, we have asymptotes at both plus 2 and minus 2. Which means that c of x must be graph 1. And that's it. So in the next example, we are going to consider more functions with more than one vertical asymptote. And we can see that the first function, y is equal to 4 over x squared minus 4, the denominator can be factored. So we can rewrite this function as y equals 4 over x plus 2, x minus 2. Notice also that the degree of the numerator is less than that of the denominator. So it also has a horizontal asymptote at y equals 0. Okay, so we can go to the graph and add the asymptotes in. And to complete the graph, we will use a table of values. And we're going to choose values that are close to the vertical asymptote. So we're going to let x equals to -3, which gives us 4 over 5. And then -1, which gives us -4 over 3. We can let x equal 0 as well, which gives us -1 for the y value. And then finally, if we let x equals to 1 and 3, we will also get 4 over 3 and 4 over 5, respectively. So now we can go ahead and plot all these points. And finally, we can connect all the points using a smooth curve that approaches the asymptote as x gets to be negatively large, positively large, or close to the vertical asymptotes. That's it. So the next example is very similar. Right, we end up with the same asymptotes of +2 and -2. And once again, the degree of the numerator is less of that of the denominator, so we also have an asymptote at y equals 0. Because if we try dividing to find the horizontal asymptote, we get 0. Just going to go ahead and add those in. And just as before, we're going to find additional points using a table of values. So -3, -1, 0, 1, and 3 for the values are close to the vertical asymptote on either side. In this case, we get -3/5, 1/3, 0, -1/3, and 3/5. Okay. We can go ahead and plot those. And once again, we're going to connect the points with a smooth curve and using the asymptotes. So this graph will have 3 parts, just like the last one. However, the shapes will be a little bit different. And finally, we can fill out some properties of both graphs by looking at their x-intercept, y-intercepts, and vertical and horizontal asymptotes, just to summarize what we saw. Y was -1. There are no x-intercepts. Okay. Vertical asymptote at ±2. Horizontal asymptote at y equals 0 for the first graph. And then for the second graph, the x and y-intercept are both 0. And then we have the vertical asymptote once again at ±2, and horizontal asymptote at y equals 0. And that's it. So today we looked at how to find the equation of a rational function given its graph. We look at how to match different rational functions, the graphs to their equations. And finally, we looked at a situation where we can have multiple vertical asymptotes. And that's it for today, so thank you for listening.